Hello everyone, today we'll talk about the solution to the problem minimum number of operations to sort a binary tree by level. This is really two problems in one, because we have to sort every level of a tree and we can only swap nodes within the same level. Maybe the problem would be more interesting if we could swap any two nodes that we want, but no, every level is independent, so really the problem is first to generate a list of nodes at every level, and then for every level we have to calculate the number of swaps that are necessary to sort that level, and the sum of those is our final result. The first part, generating lists for every level, is very easy. We'll be keeping a list of lists, and we'll be having a recursive function that takes a node and the level of that node. So we start with root and 0. And now we have to make sure that the appropriate list for our level exists. So if the length of levels is less than or equal to level, we have to generate a new empty list and append it to the two lists of levels. And now we append the value of our node into levels of level. And we go into our left and right subtree with the level being increased by 1. Very simple. And of course, since I've omitted here a check whether or not the node is null, we have to make that check here. And one way of doing that, instead of writing if node left, go of node left level plus 1, we can write node left and go. Node right and go. This is part of the behavior of Boolean binary operations that might be quite surprising to people. So you can write something like this. If you write this and this, then if this is false, then this never executes. If this is true, then to make sure that and is true, we have to execute this part, so it executes. Also, by the way, those binary Boolean operations, those operators return the last thing that they had to evaluate to get the value for this whole end. So if this is false, it returns the value of this. If this is true, then it has to check this. So it returns the value of this, whether it's false or true. But that's just a digression. And the second part is the cost for a given level. And now, this is quite interesting, because if you've never thought about it, how many swaps you need to sort an array? Maybe a basic idea would be that, well, we can look at how many numbers are not at their correct position, and so since we have to move them, then the number of such nodes is the number of swaps. But that doesn't work. For instance, if you have a list of 1, 2 and a list of 2, 1, then there is only one swap needed to change one into the other. So a list of the form 2, 1 has two nodes at wrong positions, and you can swap them in a single swap. You can sort that array. So it's not just the number of nodes that are on wrong positions, and it's not even that closely related to that number of nodes. If you're interested in it, you can look up permutations, you can look up how to split permutations into cycles, and then, if you think about splitting permutations into cycles, you can pretty easily come up with the, let's say, where the number of operations really comes from. So how the number of operations to sort an array, to sort a list, is related to the form of its split into cycles. So how many cycles we have, what those cycles are. And here we don't really care about that theory, because we can simply simulate the process. But to convince ourselves that the simulation will work, that we can do what we're going to do, what I'm going to show in code, it's good to know that cycle notation, and also to know what happens when we swap two numbers, what happens to this cycle representation of a permutation. But enough of those digressions. Our function that takes a list, so this is our level, and returns the cost, which is here res. The only thing that we need to do is essentially go through the original list and the sorted list. And whenever we see an element that's not sorted, we just swap it into its correct position. So when we, for instance, see a position, we want a 5 to be there, but there is a 7 there, we swap that 7 with our 5. So to be able to do that, we have to have a mapping in our original array of the position for every value. And now for every position in both of those arrays, if the appropriate element is already there, we don't have to do anything. Otherwise, we have to make a swap. And to make a swap, we have to use this mapping dictionary. So this is essentially just swapping those two positions, but we have to actually maintain those mappings, and we have to use those mappings to get to the element. So these are those swaps. Probably we wouldn't have to do half of that because we don't care really about what happens here at position I after this swap. We only care about the position later that we're using to swap. And you might be wondering, because I mentioned that the result is not just the number of values that are not on their correct positions. And here it's something like, for every position, if it's correct, continue, otherwise increase result by 1. So what's happening here? But the crucial part is that we actually perform the swap. And this swap disrupts what's happening later in the array, and it captures the fact that actually fewer swaps may be needed. So those swaps might actually make and will actually make sorting the rest of the array easier. By the way, one easy thing to see here about those cycles and so on is that it's impossible to have an array where exactly one element is on the wrong position. So that's also an interesting observation. Of course, the final result is sum of cost of level for every level in our levels, and that's it.